Hello, our team is formed by Lizeth Lopez, Juan Ignacio Honold, and me, Jessel Banda. And today we are going to be presenting our experiment on optimization of biomedical machining based on the article Wire Electric Discharge Machining Parameters on Surface Roughness of 316L Stainless Steel using Full Factorial Experimental Design.
Now, in order to understand our experiment, we have to first understand the materials we are using in our experiment. First of these materials would be the 316L stainless steel. This material is widely used in orthopedic and dental implants and cardiovascular stents in biomedical and engineering applications. It is especially used in medical implants that require high strength of substrate plastic deformation, such as bone plate or screws. In recent years, many attempts have been made to improve the surface properties of metals and alloys used in biomedical applications.
The procedure used in this experiment is wire EDM, one of the most extensively used non-conventional material removal processes, as it provides an effective solution for machining hard materials with complex shapes, like the 316L stainless steel. On the side, you can see a diagram showing the EDM cutting procedure with the 316L stainless steel plate and how the part is CNC movement controlled.
Now we move on with the experimental design. First, the experiment investigates the effect of surface roughness on the most influential EDM parameters on the 316L stainless steel material. First is the ton, the pulse on time, then the peak current IP, then the servo voltage, the SV, and finally the wire tension, WT. The EDM is the electronic distance measurement, and it determines the length between 2 points using electromagnetic waves. The analysis of variance, the ANOVA test, was used to determine the significant factors and regression analysis to establish the relationship between factors and responses. The machining was done on the JAPAX LDM 50 CNC machine on 316L stainless steel material, as it is shown on our infographic. The wire electrode applied is brass wire of 0.02 millimeters diameter. The size of the material taken is 150 times 150 times 50 millimeters. The rectangle piece was then cut across the cross section to produce specimens cut based on the parameter combinations set using Taguchi design. For each factor, two levels were considered using full factorial experimental designs, as it is shown in the table below. The first is the pulse on time, which in level 1 is 15 and in level 2, 25. The next one is the peak current, which is in level 1, 9, and in level 2, 12. And the servo voltage in level 1 is 5 and in level 2, 15. And lastly, the wire tension in level 1 is 5 and in level 2 is 12. The confidence interval level of 95% was used throughout the analysis. Now, on the table shown below, we can see the acquired data used in the experiment.
As you can see in the table, first you can see the levels of treatments used in each of the factors, and you can see the two separate replicates were applied to the surface roughness in microns.
Now, for our analysis of variance, we input our data into the Minitab software, where we first had an initial analysis of variance that gave us various factors that were statistically insignificant to the experiment. These factors were removed with pooling. The factors that were removed included the servo voltage, the pulse on time with servo voltage, the peak current with the interaction with our wire tension, and the pulse on time, the interaction with the peak current and the servo voltage. All of these were removed because they had statistical insignificance. Now, to move on, we conducted our second analysis of variance. This analysis of variance gave us, as we can see, the data we have in our analysis of variance shown. The factors that were statistically significant included pulse on time, peak current, the wire tension. The two-way interactions were the pulse on time with the peak current, the pulse on time with the wire tension, and also the peak current with servo voltage and servo voltage with the wire tension. Our three-way interactions included the pulse on time with the peak current and the wire tension, also pulse on time with servo voltage and wire tension, and also the interaction between the peak current, servo voltage, and the wire tension. Now for our four-way interaction, which was statistically significant, it's the pulse on time, the peak current, servo voltage, and wire tension, all of them together. Now we could see with our results in our Pareto chart for the standardized effects with using our confidence level of our alpha, which is 0.05, we got that the most statistically significant variable would be our variable A, which is the pulse on time. This gave us a weight distribution of 35.55% for our standardized effects. As we can see also for our model, we adjusted it accordingly to the observed values with a R² of 98.2%. Now, as we move on, we could see our regression equation in coded units, which has all of our statistically significant values and their interactions. Then to move on, we could see our normal probability plot, which gives us a normal distribution for the residuals and percentages. Then our final plot, which would be the residual versus fits plot, gave us a confirmed equal variance for the duration of the plot.
After performing the analysis of variance on our two-level four-factor design, we conducted also two different plots, a surface plot and a contour plot. The following plots depict the influence of the factors analyzed on surface roughness. Since the experiment is focused on surface roughness in medical-grade stainless steel, the objective is to minimize the surface roughness response. First, the surface plots visualize the relationship between the surface roughness and the two variables at a time, while keeping the other two variables constant. We have two different things that we can observe in our surface plots. First, we have the surface shape, which indicates how the surface plots changes with respect to two variables. A steeper slope means a more significant impact on surface roughness, and with color coding, we can see the representation of the magnitude of the surface roughness with darker shades indicating higher values. Then we have our contour plots, which show the surface roughness changes with respect to two specific variables. Regions with darker blue colors indicate lower surface roughness values, meaning smoother surfaces, and regions with darker green colors indicate higher surface roughness values, meaning rougher surfaces. The shape and orientation of the contour lines reveal how the two variables interact to influence the surface roughness of our experiment. Here you can see in the surface plots and in the contour plots that the interaction between the peak current and the pulse on time with a high value on both of them portrays a higher surface roughness, meaning a rougher surface on the stainless steel, and a lower value on both of them portraying smoother surfaces on the steel. On the second contour plot, you can observe that the servo voltage in this case is not significant to the surface roughness on the stainless steel. However, the pulse on time portrays a smoother surface with a lower value. Then we can see our wire tension in respect to our pulse on time. You can see that with a higher wire tension and a lower pulse on time, we get a smoother surface. In the fourth and fifth contour plot, you can see that a higher peak current indicates a rougher surface. The fourth one with a higher servo voltage or a lower servo voltage, it doesn't make a really big difference. However, a lower servo voltage in this case will be more ideal. In the fifth contour plot, you can see that a higher wire tension is better in this case. And in the sixth contour plot, you can see that a lower servo voltage with a higher wire tension is the best recommendation for the surface roughness in this case. So our final recommendations are for the peak current to be set on a low level, the pulse on time to be set on a low level as well, the servo voltage on a lower level, and the wire tension on a high level. If you want to look more into the stainless steel or the EDM cutting, you can click on our links, and this is all for our part. Thank you.
Thank you.